Welcome to another Math Counts hour. And today we're going to work on the 2012 State Team Round. So we're going to be working on the hard problems. You ready?
Okay.
Let's start with number 1. Well, the student council sold tickets to the school's annual carnival. Adult tickets were $5 and student tickets were $2. They sold 5 times as many student tickets as adult tickets and raised $1,125. How many tickets were sold for the carnival? Do you have an answer?
Almost. I feel like this number is big, but 450?
Yeah, that's what I get as well. I'm going to go ahead and finish my equation here.
It was kind of big. It felt kind of big.
And so the total number of tickets was n plus 5n, which is 6n, which is 450 total tickets when we plug in n equals 75. Okay. Good work. Number 2. Every CD at Bargain Warehouse is sold for one of 3 different whole number dollar amounts. Customers each bought 3 CDs. First customer spent $4, the second customer spent $9, and the third customer spent $12. No customer purchased 3 CDs of the same price. What is the price at which Bargain Warehouse sells the most expensive CD? Tell me when you get an answer.
Okay. Oh, 5.
Yeah, I got 5 as well. How'd you work?
I kind of set up an equation, and then I just guessed numbers kind of randomly.
Okay, that's one way to do it. We could let the prices be like A, B, and C, try to work it that way. I saw that 4 is a highly constrained number. And so, if there's 3, well, this is less than 3 times 2. So the only real way we could do this is 1 plus 1 plus 2. And that gave me a lot of information. I already knew 2 of the 3 prices. So it was really just a matter of finding the third. And 9 could have been a number of things. It could have been 1 plus 2 plus the new price, or 1 plus the new price plus the new price. It wasn't 2 plus the new price plus the new price, because that would be the maximum possible, allowed. It could also be 2 plus 2 plus x, which is what I wound up using. So there were different possibilities for 9. But I said, okay, 12 kind of has to be above any of these. So x plus 1 or 2, but it's going to be an even number right here. So this had to be even. So I said, okay, 2x plus 2 is 12. So x had to be 5, and I just wanted to make sure. So I plugged in that as a possibility and saw that it worked. So 5 is our answer. So what did you learn from that?
Kind of use the numbers more. Like, think about it some more sometimes.
Yeah, in particular, this right here, this is a version of the extreme principle. If you notice something that is highly constrained, that is at a boundary of possibility, like a minimum or a maximum, then we're more likely to be able to use that information in isolation or learn something important from it. And that leads to a quick solution sometimes, or an easier solution in others. Okay, let's take a look at number 3. When one integer is removed from a list of 5 integers, the mean of the remaining 4 integers is 3 less than the mean of the original 5 integers. What is the positive difference between the mean of the original 5 integers and the integer that was removed?
x5 is 12.
It's not 12, but what are you actually saying?
Wait. X subset 5 is 12. Wait, no.
What is the problem asking us for?
Oh, it's asking for the difference between the mean and the original 5 integers.
Yeah, and that is 12.
12.
Yeah, and if I were working this problem, I would have probably written this down without even writing down, without even interpreting the information, because we can relate means to totals so easily, just the number of values times the total. But there's also a way to do this quickly. The moment I read this problem, I knew that the answer was 12. I knew that it was 3 times 4. How could I have known?
Since it was divided by 4 and divided by 5.
Sure, but what does that mean?
Once you subtract, it has to be 12 more than the mean.
Let's say that we've got a mean of the first 4 integers. It's some amount. I'll put like an axis here. some amount. And if we add some other number to the list, we get a higher amount. In this case, it's a higher amount by 3. Well, here's the thing. That new number, in order to, let's say that we wanted to add something to all the previous numbers to bring it up to the level of that new mean, we would have needed to add 3 for each of the 4 of them.
So then that's just 12 in total.
Yeah, in order to bring them up to whatever that other number was, so that they would all have the same, so that the old group and the new number had the same mean, meaning that the mean of the old group was the new number. We would have had to have raised the total of the old number by 12. So that's a quick way to use what we call the baseline method to come up with an answer. Okay, let's take a look at number 4. The legs of a right triangle are in the ratio 3 to 4. We've heard that story before. One of its altitudes is 30 feet. In square feet, what is the greatest possible area of this triangle? Express your answer as a decimal to the nearest tenth.
Similar triangles.
You can use similar triangles for sure in multiple different ways. There are infinitely many right triangles that have these proportions. If one of the 3 altitudes is 30 and you want to maximize the area, which one of the altitudes do you want to make equal to 30?
Oh, 3x or 4x.
Or?
Wait, what? I think those are only 3.
There are 3 altitudes, 3x, 4x,
and
and
h.
h. Which one of those do you want to make 30?
H.
Why?
Since it's the smallest out of them all, and it'll maximize the area.
Why do we want to pick the smallest one?
If it's the smallest one, then the other ones will be bigger than the other choices, and then it'll have a greater area.
That's good intuition. I think that you understand that on an intuitive level.
Mhm.
Let's come up with a good solid computational reason. The area of the triangle is base times height divided by 2. So if we know the height, what are we trying to maximize in order to maximize the area?
Maximize the base.
We want
Times.
the biggest possible base to pair this with. Okay. Well, how do we find h if the sides are 3x, 4x, and 5x? What is h? We know h is 30, but we want it related to x.
Not sure how would you solve it from here?
Well, we have multiple ways of finding the area, right?
Yeah.
I call this the fundamental principle of algebraic problem solving. If you can find 2 ways to compute something, you have an equation. What are 2 different ways to compute the area of that triangle?
5x times h divided by 2, or 3x times 4x divided by 2.
So what is h in terms of x?
Um,
Or what is x in terms of h?
h is 12x divided by 5. Oh, and then you can solve it.
Or x is 5h divided by 12. We're given h. So now we can compute x.
So then it's 25 out of 2.
And we know the area is 6x squared. What's that equal to as a decimal?
Hmm. 337.5.
You're a little bit off.
Oh, that's where I missed. 7.5.
That's right. You squared 15 before, didn't you? Instead of 25? Is that what happened?
Yeah.
Yeah. All right, that's good enough. Okay, let's take a look at number 5. Let me know when you think you have an answer.
Oh, sorry, I was muted. I got 15.
Okay, good. Yeah, really the biggest thing is setting up the equation here, isn't it? After that, and really we didn't even have to solve the quadratic, did we? We can just, the numbers are such that we can just play with them and say, hey, we need the product of two consecutive integers, and it could be -8 and -7, but we're sticking with positive integers and we add those. 7 + 8 is 15. Okay?
Mm-hmm.
Moving on to number 6. How many ways can 18 be written as the sum of 4 distinct positive integers? Interesting.
680.
I think it's fewer than that.
Might be overcounting.
How'd you get that number?
I just gave I made like 4 different separate places, and then I gave 1 to each of them since they have to be positive. And then I just used stars and bars and did 18, but I forgot about the distinct part.
Okay, yeah. Tougher to use stars and bars here unless we can find a way to be clever.
Casework?
Possibly. What's your idea with casework?
Go from 1, 2, 3, 4, 5, 6, 7, 8. Just go up.
Go up with what?
Move A up 1 and then just keep going.
Okay, casework based on A.
Yeah.
I like it. Okay, A equals, do you want to start with A equals 1 or do you want to start with the largest possible value of A?
Probably the smallest.
Okay. I'm going to go ahead and tell you this is the hardest case, so if you can make it through this, we're good. So A equals 1. What do you notice?
B equals 2.
B is at least 2.
And then C is greater than B.
Mm-hmm.
And then D is greater than C.
Okay. Even before we get a sum of 18, just by the fact that these are distinct, we know that A plus B plus C plus D is at least 10. And maybe we can make B, C, D. Maybe we can try 2 and 3. What is D?
C is. Wait, should we just set B as 2 and then go down, or?
Yeah, subcases.
Yeah.
So we have the B is 2 subcase. We get 1, 2, 3. JV and C are 1, 2, and 3.
And
D.
12.
Okay. Keep going.
1, 2, 3, 12.
And 1, 2.
4, 11.
Okay. How many of these are we going to have?
Wait, are we gonna count the ones 1, 2, 12, and 3?
You tell me.
Yes.
Is 1, 2, 12, and 3 different than 1, 2, 3, and 12 in the way the problem is asked?
Yes.
And how many ways can 18 be written as the sum of 4 distinct positive integers? So that's interesting.
It says they could be counted as different integer at different.
Okay, you're right. They can be counted in different ways. But I'll say this, I would rather count them as 1 and then deal with that at the end. Why might that be easier?
Wait, can't you just reorder them?
Exactly.
4 factorial.
4 factorial. Exactly. So, we can break symmetry by ordering them ourselves. That's what I did right here. And I should have talked about that at the time, but that was my plan. To count them given that limitation, and then permute, since they're all distinct, we can permute them all the same way very easily. So it's like we've got 5 in this subcase.
Mm-hmm.
What about B equals 3?
Um, 10.
How many of these are we going to have?
6, 8 is the last one.
Good. That's
So
what I'm
there is
do. Yeah, find the first
3.
one and the last one, and that makes it easier to count more quickly. Okay. B equals 4. How many do we have?
6, 7, 2.
Just 2. Okay. Do we have anywhere B equals 5?
No, since it's smaller than 6, D is going to be smaller than 6.
Okay. So for the case A equals 1, we have 10 possibilities. Okay. What about the case where A equals 2?
Um, 9.
Okay.
6, 7, I think.
And we have 1 in between. So we have 3 total.
Yeah.
Okay. Are there any more?
7.
Is that the only one?
Yes. I don't think there are any more.
There are not. If we go to 2, 4, 6, we get 2, 4, 6, 6, and that doesn't work. Okay. A equals 3.
I will be back. I need to go get something.
Yeah, go ahead.
Okay.
Okay. I went ahead and just did the one simple possibility for a equals 3 because all the numbers jammed together, 3, 4, 5, 6, already add up to 18. And do we need any more cases?
No.
No, 4, 5, 6,
4,
7
5,
is already
6
too big.
is 1 away.
So we have 15
No, it's,
total.
yeah.
So what is our answer?
Um, 40, no, 360.
360 is our answer. Very good. And there may be some clever fix to stars and bars. I'm going to leave that as an assignment.
There might be.
There might be. At the very least, we could do something like principle of inclusion exclusion
Ooh.
and subtract away, combinations of the different sets where some, 1 or 2 or 3 of them are repeated. That's a possibility. Okay, let's take a look at number 7.
Be in the center, right? To minimize the distance.
Somewhere near the middle, that's for sure. Hmm.
Draw the straight lines connecting B and D and C and A. And the point where they meet is P,
I like your thinking.
because that minimizes the distance.
So exactly how does that minimize the distance?
Because a straight line is always the shortest way
Yeah.
between
We
2
were to
points.
travel from A to C, and we want to put some point P along the way. If we were going to go outside of that line segment and come back, we know by the triangle inequality that P would need to be on that line in order to achieve the shortest path, because the sum of those two distances must be at least as large as the straight path in between. Good. The shortest distance between 2 points is a straight line. Okay, we want the intersection between those two lines because those two lines will minimize the two pairs of sums themselves. So what is that intersection? How do we find that?
How do you find where they meet?
How have you ever found
Wait,
intersection point between two lines?
they're using their equations.
Using their equations, okay. What are the equations of these lines?
Find the slope first.
Okay. Slope of one of them is 2/3.
Uh, 7 minus 2. -2.
Okay.
For AC, B is 0, and 14 for B2.
Oh, you're close. Let's be careful. Plug in any one point.
Oh, 16.
Okay. So now how do we find the point of intersection?
Solve for x. Subtract the second equation from the first.
We could subtract the equations, or we could just say, hey, let's use transitivity. Y equals both of these quantities.
Oh,
Let's just equate them.
yeah.
So what do you get?
X equals 6.
Okay, so what's Y?
4.
Yeah, it's easiest to use. Y equals
Yeah.
X. So we have the point 6, 4, and that is the correct answer. What did you learn from this one? You got a good start. You got the hard part early.
Yeah. Draw the straight lines.
And remember that, remember to get the algebra right. Organize it well, and plug in a point. Make sure, and maybe even plug in both points to make sure that you get B2 correctly. The first one was easy because it goes through the origin, but make sure that you get your right. Okay, number 8. A hot air balloon will slowly start to descend toward the ground at a constant rate of 15 feet per minute from an initial height of 1,200 feet.
I feel like we've done this one before.
Have we? Maybe you've done it separately.
It was like
you have done it. I don't know.
Kind of. It was like in the 20s, not like 8.
Maybe we've done a similar one, or maybe you've done it separately for me.
Yeah. Oh, fine. 295 divided by 63 minutes.
Say that again.
295 divided by 63 minutes.
Explain to me what you're doing.
I found their how fast are they coming towards each other, which is 315 feet per minute.
Okay, I agree.
And then the distance
Hold on one
is
second. So you're definitely starting out right with this one. I just want to write this down. In order to have the rates normalized, we convert the second one to the first. Now we have things in minutes, which is nice because we're supposed to give our answer in terms of minutes. And now we have relative rates of 300 feet per minute and 15 feet per minute. So the relative rates together are, they're moving together at a rate of 315 feet per minute, and they need to cross a path of 1,190 feet. So we have a rate, and we know multiplied by time gives us the distance. So we want that time in minutes is going to be 1,190 feet divided by 315 feet per minute. So 1,190 divided by 315. Of course, you've got a calculator in this situation.
got it missed a little bit.
Sorry?
I missed it by a little bit. Probably did the division wrong. Yeah, I think I did the division wrong on accident.
Yeah, when you said 295, I wasn't sure where that came from. Maybe you started with 1180 or did something slightly different. I'm not sure. But do we agree?
I got the same numbers, just I divided it on accidentally wrong. Yeah.
The same number of minutes? Okay, what is that as a decimal? Rounded to the nearest 100.
3.78.
3.78, and that is correct. Okay, so tell me where you were going wrong and how you can correct that mistake. You had the setup right. You had the right idea of having the two rates add together so that you just have one relative rate.
I divided 1,190 wrong on accident.
Okay. So if you were working with a team, what would you have been doing with your own scratch paper, out of curiosity?
I kind of did the same thing, but without the drawing.
Okay. Because it's the team round and you get to rely on your teammates and they get to check your work, I would say write out your work even more organized than you ordinarily would on your scratch paper. Make sure that it's nice and organized and readable. Your ability to communicate becomes more important when you're working with a team. Okay. Number 9, there is more than one 4-digit positive integer in which the thousands digit is the number of zeros in the 4-digit number. The hundreds digit is the number of ones, the tens digit the number of twos, and the units digit the number of threes. Find the sum of all such integers. Interesting.
Numbers of ones, numbers of two, and numbers of threes. Whoa, this is complicated.
It is, isn't it? Using all that information. Do the digits have to be 0, 1, 2, and 3?
Uh, 2010. Just
2010. No, that doesn't work.
oh,
Could you have a digit other than 0, 1, 2, or 3?
no,
Why not?
because then it'll cover up all the other spaces.
Yeah, if you were to put like 4 someplace, like 4 2s,
That's just gonna cover up the
tens
whole
digit was a
room.
2, then, sorry, the tens digit were a 4, then you would have to have 4 2s, which is impossible because one of those 4 digits is already a 4. So we can't have 4 or higher. Okay, so good. We have good constraints. That makes life feel a little bit easier. This doesn't feel quite so impossible now. Just 4 possible digits. Now that we've constrained the digits, what might we do?
Test some of them.
How so?
Try testing.
Plug in numbers, but we have 4 times 4 times 4 times 4, 256 possibilities still.
But some of them don't work.
Some of them don't work. Hopefully a lot of them don't work. How about this? What if we do casework on the number of zeros? We know that the leftmost digit can't be a 0.
Yeah.
So what if we let it be 1? There's going to be 1 0 somewhere in here. And it can't be the next digit because we already have 1 1. So the next digit is 1 or 2 or 3. No, I don't think we could have 3. What if we made it a 1? 1 0 1 1. Oops, nope. Then we'd have 2 1s already. We'll make it a 2. So we're going to have 2 1s. We need a 1 somewhere and a 0 somewhere. But we already have 1, 2, so that would have to be 1 and 3s. None. 3s are going to be hard. In the same way that 4 was impossible, 3s are very constraining. Okay. Is this the only number that we could have made starting with a 1? Did we limit everything?
Yes.
We could try to put a 3 here. That would mean 3 1. So everything else is a 1, but there are no 2s. So that's a lot.
That doesn't work.
And we haven't included a 0. What is the sum of the digits?
4.
Yeah. It has to be the number of digits.
Oh, yeah.
So that's a pretty big constraint. Well, what if we try to make 2 zeros? What do we know about the remaining digits?
There has to be 2 1s.
Really?
Wait.
We're going to have 2 zeros and 2 1s and a 2?
Wait, no.
We have to have 2 zeros somewhere out here.
2 zeros and 2 2s.
It's going to have to be 2 zeros and 2 2s. And that tells us where the other 2 has to be.
Right there.
Yeah, so is this it?
Yes.
And if we have 3 zeros, well, they'd all have to be zeros, but those don't add up to 4. We'd have 1 3 already.
Yeah.
That's impossible. So I think it's just these 2, huh? Did we do anything wrong? I don't think we did. That is the correct answer, is 3,230.
I like that one. Good logic problem. Forces us to find ways to constrain the possibilities. And finally, we have problem number 10, which is going to be our hard geometry problem for the day. 3D geometry. It's the mothership. It's the boss. Okay, what is the volume of this frustum? Before we take a look at the specifics, how is it that you want to find the volume of something like this in general?
Wait. I don't know.
I mean, how do you get a frustum? Where does that even come from? It's the frustum of a right cone. What does that mean?
Wait, oh, you solve for the big giant cone and then you chop off the top part and you have that
Yeah,
frustum.
yeah, exactly. This comes from having a cone and then chopping off the part above it. So that's our goal, is to figure out the dimensions of the big cone and the little cone. And we know the little cone has radius 8 on the base. We just need to figure out heights, don't we? Well, we've got some numbers in the diagram. What do we get out of that? It's a right cone, so we have a right angle right there. So what do we know?
How do you find the area of a cone?
How do you find the volume of a cone, you mean?
Yeah.
The volume of a cone is the area of the base times the height divided by 3. Just with a pyramid. Base times height divided by 3.
What is the height, though?
What is the height? Okay. Maybe we can come up with that.
That's going to be one of the challenging pieces. What else do we know other than the numbers that are given in the diagram? Can you come up with any numbers?
AB is 9.
Yeah. We have a distance of 9 right here.
Yeah.
I'm going to let h be the height of the small cone. So h plus 9 is the height.
Similar triangles.
Ah, good. Very good.
That's the big key. When we're working in 3 dimensions, we want to take cross sections where we can sometimes. And in this case, you have spotted these similar right triangles because they share an angle and they also have the 90-degree angle, AA similarity. So what does that tell us?
9 plus h divided by 12 equals h divided by 8.
I'm going to write mine down slightly differently. So h over h plus 12 is 2/3, cross multiplying. 3h equals 2h plus 24. So h equals 24. And that is the height of the small cone. So on a computational level, what do we do next?
Solve. Just solve.
So to solve,
Yeah.
what is our computational setup going to look like?
The height times 24 times 64 pi divided by 3. And then subtract off 33 times 24 squared pi divided by 3.
Yeah. Reverse the order at which you're subtracting off, though. Wait a minute. Pardon. I solved wrong. Do you see what I did? These aren't the right numbers.
Wait.
I had a brain fart. Look at my equation setup. I did something wrong.
Wait a second. You did plus 12.
In that denominator.
Oh.
Yeah. That is, it's always good to check over your work, right?
Yeah.
And I'll tell you why I noticed that. I noticed that because I was like, wait a minute. 24 to 33 didn't look right. Like that should have been 2/3. So it's good to be exercising your number sense as you move through. That way you can catch a mistake like the one I just made. I probably made it because I was talking and reading at the same time. But it's good to have automatic checks, like a habit by which you check things. So now, 18 plus 9 is 27 is the height of the big one, times 12 squared pi divided by 3 minus 18 times 8 squared pi divided by 3. And here's what I'm going to do. Here's the thing. These are similar cones, and we have a 2/3 ratio. So what we're really doing is taking a volume and subtracting 2/3 cubed of that volume. Do you see that? I mean, like we could just do this computation, and that's going to give us the answer. That'd be totally fine with me. However, because of similarity, we might be able to do the arithmetic a little bit more easily.
Oh.
Like that. In which case we have 19 over 27 times 27. They may have even set it up to make it easier for us to do it this way, because those 27s now cancel out. Then we have 12 squared, which is 144 over 3 times pi. All this right here becomes 48 pi, and now we have 19 times 48, which is 20 times 48 minus 48. 960 minus 48 is 912, and 912 pi is the final answer. So I just wanted to take you through that at the end because, it's perfectly fine to compute. We'll get there. But it's good to use similarity in as many ways as you can. Sometimes it simplifies things. Sometimes it's just a good reminder or a second way to perform the calculations. All right, any questions or thoughts?
That was interesting.
That was interesting. 3D objects get easier with experience. This wasn't as hard as you thought it was when we started. Yeah, you actually found the hard part. I think the hard part of this problem with this type of 3D problem is recognizing the cross section and the similar triangles. And once we were there, once you've gotten past your fear and we had the diagram, so remember that. Remember that. If you get past your fear and you work with that ugly object, you can get there on your own.
Okay.
All right, let's call it a night.
Thank you.
You're welcome. See you next time.
Bye.